Hello and good evening. In the previous video, we had stopped up to here. That is, we saw how to do profile peak matching or let's say pattern matching in expert high score to know what the structure or the material is. Let's say now you want to do, or let me show why you should do Rietveld first. See this? Okay, I'll remove these shadows. See this? There is a slight mismatch between the peak and the position of the selected pattern, and this is also there in nearly all the peaks. If you zoom in enough, there is a very slight difference, which means maybe your ABC parameters are not exactly the same that is found in the this reference material. This happens generally, every time this happens because of some synthesis conditions, and these are ideal samples cloned under ideal conditions, all these reference samples. So this is the ideal pattern that should come, but then you have some deviation, which means some changes in ABC parameters or a bit of strain or stress, something like that. So you can't just mention if you want to do it correctly, you can't just mention that my ABC are just 4.24 angstrom. So you need to find out what your sample uh, ABC are. For that, you need ritual refinement. That is what generally ritual refinement is. You fit a mathematical model to your data, and then there are many parameters in the mathematical model, a lot of them. So once there is a very good fit in the ritual, so which means that you have mathematically fitted your pattern. So whatever the parameters that appears in the mathematical formula or the model are the parameters of your material. So you can get to know A, B, C, and then all the stress, strain, fitting, and then atomic site fraction, and then atom positions, everything you can fit. So how to get started with 312 refinement? Just keep this open, keep this handy. Expertise code uh, this analyzed pattern. Go to the software I prefer is Foolproof Suite. This is free of cost available. So first you open this Foolproof Suite, you see a lot of programs available here. Initially go to this blue color. Blue colored Run Win Plotter 2006. Open this. It will open. It's a legacy software. 2006. There's a better version. The just beside the button is the higher version. But this has a very useful task, I should say. Uh, to mention again, while we did this um, while we did this expert analysis in expert high score, I told or we took the format in .raw format. So for Rietveld, it's better to have it in .xrdml. So for a minute, I'll just convert PowerDLL. I'll show you how to convert in this. Just say open sample one raw, save as. Here I'll select xrdml. So sample one xrdml, save, convert. If you have multiple files, use this. So it has come XRDML. I'll just change the name because I know it's magnesium oxide, MgO. Okay, doesn't matter. You can put sample one or whatever you want. MgO. I just open here MgO XRDML. It has opened. So now you can see all the pattern is plotted. Just go file, save data as free format.dat. You would have seen many YouTube tutorials or many places on the internet where they say that you open an Excel file, write the first column as the 2 theta position, then erase some columns, then again write something else, use tab, do it in Notepad, Excel. I've tried all those, and I found that this is the easiest. You don't need to do anything. Just open in WinPlotter 2006, save it as .dat file. I'll just put the same name, mgo dot dat. Yeah, just make sure that you put this DAT in capital, else it takes small letters. It doesn't matter, but customarily people have been using .dat, so I've been using that. Save. My pattern is saved. Just close this now. Now for the second part, go to this white color. That is the more run print plotter. This is a more advanced one compared to this. This lazy one, this doesn't, but you know, this more advanced one doesn't have that save data as format, like let's say .dat. Only this one has. So it's a very useful thing to have. Once you open this file, yeah, in the green color you would have noticed we use the open button. If you use open button, nothing comes up. So better to go like this way. File, open raw data file, second option. Then at the end there is XRD multi-scans. Just do OK. XRDML, countings. So the pattern is open here. Now you do point selection, automatic background. Let's say just put OK. It has taken a fairly good background. Okay. For now, I'll not be doing much of a this one to this background. Still, let's say I'll again select the background. So this is one way of selecting the background. Once you do that, you just say save background points. Yes, and put some name and then save it the background points. Let's say I don't want. I'll do it again. Let's say the background points are not taken in a nice manner, or you like to make your own background. What do you do? Point selection, select background points. Then just you can trace the whole background whatever you have. Yeah, and while doing this, let's say you get to the peak here. Don't put a point in the middle because when you refine it, maybe it goes up, your refinement is wrong. So put it one at this end and one at this end. Same. You understand? Like this should be the method to select background points when you have peaks in between. Don't put a background point in here because once you put it, you refine it, this goes up or down, your background is gone. It's not a correct refinement. So for now, I'll just use the automatic background because for my sample it is giving good background. Automatic background, okay. 62 points, fair enough. Save background points. Yes, let's I just give BG background. Save. It has 62 background points. Okay, no. Close this. Now comes the main task, creating the EDPCR file. This also in YouTube tutorials and all you would have seen many places they are teaching you how to. I'll tell the easiest method. Generally people also use this load CAF file, that is they take a CAF file, make the PCR. Sometimes I've done this, but sometimes if it goes wrong, it just keeps analyzing the CAF data. The most workable method, that is what I'll be telling here. Go new, general, title, MGO. It is better to keep all this name constant, the file name, the project name, and everything. So, and the program name. Once you save it, you just tick this box, optimize calculations. Okay, patterns, add a pattern, data file. You can have free format to theta, that's what we created, browse. So you have Rietveld, mgo.dat. Then you have refinement, simulation. You don't want to do simulation. Simulation is when you want to simulate a pattern, not refine a pattern. So you tick here XRD and your wavelength, mine is copper. So you can use many peak shapes. You can use even Thomson Cox, or generally people also prefer pseudo void or any peak shape. For now, I'll use Thomson Cox as things. Theta mean. Okay, how do I know my theta mean, theta max? You can do here scan list. Okay, this value is not coming. I'll just show you. Another thing you can do is convert it to .xy. Convert your whatever data is there to .xy. So my initial is 10, step is 0.02, and it is 90. 89.99 is 90. I can consider it. So 10 theta max is 90.02. Okay. Background type. I've used a linear interpolation between set background points with refinable heights because we selected the background points. There is also an option of using polynomial functions, 6 coefficient, 12 coefficient ones. Okay. Excluded regions. There are no excluded regions for me. Geometry IRF. Yeah, if you have some resolution file, IRF is instrumental resolution file. So if you have that, if you make and you want to do stress strain analysis, then this is very important. You have to do the IRF file. Without it, the stress strain analysis won't be correct. So I'm not doing this. It's just normal refinement. Okay. Phases. My phase. Okay. What should be the phase? Name of the phase. Now, this is where the expert high score comes in handy. You have this reference pattern data. So, cubic. Here, just put calculator automatically. This doesn't matter because you just have a single phase material. It matters when you have multi-phase materials. Contribution to pattern, current phase contributes. It's an X-ray. Peak shape. We selected Thomas Cox. So, just select Thomas Cox hastings. Okay. Symmetry. Here it is given Fm bar 3m. Just put it Fm bar 3m. Yeah, whenever you input this, click symmetry operation automatic. These things should fill up on their own. M3, M192, all these things. If they don't fill up, which means then it means that you have an error in the space flow. So you need to check it again. Okay, okay. Then refinement. Put the cycles of refinement 20. Background. Let's not worry about the background for now. Let's worry about atoms first. So here I can have Mg and O, just right, Mg and O. So I just have two atoms, Mg, O, Mg, O. You can put Mg1, O1, whatever, however you want. So Mg is at 000 position. It's just FCC kind of because it's a rock salt. So BISO is 0.5. Yeah, now how do we calculate this occupancy? See, here you have 4A, 4B. That's very easy. Let's say here you have 2B and 4A. How should you calculate this? Because expert high score gives this one SOF, and here you need occupancy. So whatever the highest Wyckoff site number you have, let's say you have 8D, then and this is 4A. So 8D would be 1, and the 4A would be 4 by 8, that is 0.5. So that's how these things are decided. So for now it is 4B, 4A, so it's 1, 1. I can just put 1, 1. That's it. But let's say this is 4B and 8D, then your oxygen will be 0.5 and magnesium would be 1 because 8 is a bigger number and this is half of it. Let's say you have something else, depending on the fraction it happens. So you just have 1, 1. Okay. Profile. For now, put whatever the this is there. Initial parameters, you can say. Okay. Again, okay. Now you have done all these things. Your file is created. You have not saved it yet. This is where many times data is lost, or sometimes file is corrupted and all those things happen. This is very carefully to be done. Just click on the triple save icon. Save data as. Don't click on the single floppy. Click on the 3 floppies. So once you did this, it will ask where to save. I have my folder here. Same name, you as you type your sample name, here this thing will come up. Just select it and press backspace 4 times. That is, remove this extension. Just 4 times. Don't do extra. If you put a different name every time you run a Rietveld, it will ask you to select the file. So use the file name as the data file name as the this PCR file name. So it is better. Just do save. Just to be sure, just double tap it, the single floppy icon. Now you run it once. So your pattern is run. It gives some chi is some 0.120 e to the power 7, whatever. We know that our file is saved and nothing file corruption has not happened. Now we do each one. First, we have a background points. Okay, okay, save it. So this is how it came down or came up, whatever. How do we proceed with the Rietveld refinement? There are a set of rules on how you should refine. These are called Young's rules of refinement. So depending on the Young's rules of refinement, you should do it. Okay, so for some reason my internet is not working fine. So the first thing that we define is the scale factor in the Young's refinement strategy. If you just search on the Google, it has something in Google Images, there are many slides and also in many books it is mentioned. So using Young's method, we do scale factor first. Okay, then again okay. Save it before you run it. Save it, now run it. So once we refined scale, many things happened. It came down to 14. Yeah, and many people what they do is they see this chi-square as 1 point something, 2 point something, something, and they say that this refinement is done. No, your RP, RWP are very important factors, as important and more important than the chi-square factor. So once this is done, I just do yes. Then after scale, this zero shift. Okay, always keep this scale tick. Tick means you are refining it. So just go to instrumental zero shift, and in this, don't do zero and displacement together. Either zero or displacement, one of them. Like either your sample should have been displaced or there is some zero error. Both of them, if you refine, it's just absurd. Makes no meaning. Save, run it again. After that, linear background. Just untick it. Refine all. After that, fix all. Then lattice parameters. Just take one of them. It's a cubic one. So after lattice parameters, there is peak width. Okay, so this UVW things. This should always be less than 1, all these three numbers. V should always be negative and U and W should always be positive. Don't mess up these things. These FWHM parameters are very, very, very important for refinement. Again, after that, again, let's check background, refine. Then there is atom position, refine position. Then there is preferred orientation. So G1, don't refine G2. I don't know why, but whenever you refine G2, the whole program corrupts. I'm still trying to find out the reason, but I don't know why. Every time I've tried refining G2, whole program corrupts. So don't do it. Just refine G1. And keep it always tick like the scale factor. If you remove it, it again becomes zero, and there is I don't know why it becomes zero, and it doesn't work. So just keep it ticked. Then you have BISO. See this one, this has gone to 5.4. PISO should not be that big. So I'll again reset it. So the thing is that this is software and it does only optimization, let's say mathematical optimization only. So it is you who have to see that these parameters don't run out of range. So if something funny number comes up here, just know that you have done a mistake and rectify it. Don't go on blindly just taking B as 5 or -1 on all these things. See, whenever I try it's going 5, so I'll just leave it, which means B is not the deciding factor here, or it's not a parameter I should be refining. So now I'll go to UVW. U. Yeah, just before you do, if you have a paper, write this number down, or else just remember it 0.004. Sometimes it goes to very high 2, 3 values, so it's also an absurd value. You have to reset again. Just fine. Then I'm refining the shape parameters. So you can see this here, it is in convergence not yet reached. I again run it. Let's say even after this is the 30 or 60 cycle that is running 20, 20, 20, it's not converging. So it means that I should see this parameter and not refine it. And just put it 0. UV at a time 0.056, 0.002 in negative. Okay, does it didn't go out of range. So happy. Generally, when you refine two or a pair of these UVW parameters, these go out of range. So these are not shifting much, so which means that UVW are kind of settled. Then again I refine lattice parameter. Then I do the overall B factor here, because when we were trying to do it there in atoms, it was giving a erroneous value, like 5 or -1, something like that. So I'll be doing this B corrections here, temperature corrections. Then alpha beta won't change. Asymmetry, I'll show you how to check it. Again, I'll try once for positions. No, I'll try for once for occupancies. Yeah, see, now the whole file is corrupted. Current parameters saved in this one. So what to do in this case? This you can see something happened and it all went bad. So when this comes up, just do no. Sometimes if you are lucky, your file is saved. We are lucky your file is saved. Else you have to do make the PCR file again. Okay, so all the parameters are saved fine. Again I do background. Some instrumental corrections, same. Some more lattice parameter corrections. I'm doing lattice parameter and the U factor. And also, yes, you might have noticed I didn't touch this IG. If you do this one, it again, I don't know why the pattern doesn't fit, and whatever has fitted just goes astray, and the whole PCR file corrupts. So I'd suggest you not to touch this one. I don't know so what this parameter is, so I can't tell what it is, but I can tell you don't touch it. Okay, so now let's just do one. You can see some 3.96 it has come. I need to do some more corrections, or let's say I want to go into these asymmetry parameters. Maybe there is some asymmetry in my peaks. How do I do that? In this phases, one second, let me check where it is. Patterns, geometry, IRF. Here corrections, you have this peaks below this 2 theta limit are corrected for asymmetry. Just put the maximum, that is I have 90, so 90. When I do this, all these asymmetry parameters are activated. If you don't use this, it will give an error value saying that something has not worked or something like that. Let's see if my internet is working. Okay, my internet is not working. I can't show it. But if you go to the Wikipedia page of Rietveld refinement, you would find there many things like they would say what affects the peak shape, what affects the intensity, what affects the position of the peak. There is a table in the Wikipedia page. So depending on that, you could see what parameters you need to refine. So the reason why is not being well refined or the chi-square is not going down in as such is because there is not magnesium oxide, there is some multi-component oxide pattern. So the other atoms that are there in the multi-component oxide I have not added. I've just added one of the atom, that is magnesium oxide. So it is trying to fit but it's not able to. So once you know like uh, once you have the correct pattern of your material, like if I try to fit a multi-component oxide with the same pattern, it will fit nicely. I have done that, and I have some plots to even, I've made plots and where it fits nicely. So fit the correct material. This is just to show how to fit a material for a basic and beginner user. Once you have your data, keep trying, you will eventually get there. So let's say, okay, let's ignore that we didn't fit that correctly, and let's assume that this is fitted perfectly, and chi-square is some very good value. So what do you do after that? Go to output, CIF file, and then just do OK, save it, run once, close it. Here you have CIF file, two CIF files. We'll see which one opens. Then again, summary of RPA. One of them works again. So summary of RPA, that is defined parameter. Again run it. So in the folder that you have, you have NGO RPA, some parameters. You can see here magnesium 000.51 cell parameters, all these things. You can also find them in other things like asymmetry parameters, preferred orientation, if any, whatever we have done. All these parameters we can see here. Then there is an output file, that is mgo.out. If you open this one, here it shows everything and it's a more readable English compared to that RPA, because RPA looks more like a code. So this shows that this is the data supplied and everything, whatever it is. You can have a look, when you refine your pattern and all. It gives reciprocal cell parameters and all those things. Just copy whatever you need. You even have half width, and you can calculate all this one. I think this Scherrer, uh, this using Scherrer equation, it would have been calculated with the half width. But if not, you can even calculate on your own. So what to do with this one? Let's try opening it. Yeah, it opens. So this is the refined structure that I have. You can see now, if you observe carefully, you have ABC 4.2407. Initially in the expert high score, we had 4.2400. So, in effect, we can observe that this slight mismatch is there. That one is due to this 4.27. Maybe if we refine more better, it would have been some bigger or smaller value or something else. But you now understand why we did the Rietveld refinement and not taken this ABC values as such as given in this expert high score. So that's about refinement. Maybe in some other video I'll show you how to do a multi-component refinement. Just to show you a shorter thing, how we can do a multi-component refinement. When we add phases in here, we already have one phase. So we know we have put, current phase contribute, the peak shape, symmetry and everything. Just do add. So you get previous next. For the second thing, let's say if it's spinel, 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 contribution to patterns, current phase contributes. Then again, same Thomas Cox hastings, XRD, just do OK, symmetry, FD minus 3M. FD3 is a spinel space. So you have here M3M192 oblique. I think FD stream is, sorry, FD stream is a rock salt, I think. Sorry about that. This is what happens. You add a second phase like this. So that's how the multi refinement works, multi-phase refinement. And whenever you do refinement, here it will come, you phase one, phase two, phase three, all this will activate. Like let's say phase six is there. You can just do phase two and do it. Not a big thing. Easy only. In some other pattern, a better pattern I'll show you. And also there is a very important requirement of the data being good enough to do refinement. How do I know my data is good enough or my data is not good enough? Open raw data file. I'll just open the data once. In the foolproof manual, there is one section given on how this point should be spaced in the XRD pattern that you will get. My internet is not working, else I would have shown it. There is an image which explains clearly how this should be done. For different machines, the settings could be different. So maybe for a couple of slots or a couple of samples, you need to experiment out your settings, and then again you can figure out what is the correct setting that works for you. For me, the thing that worked is this one. Let's For me, the thing that worked is when I use 10 to 90 at 0.02 degree step, and then I use 2.5 degree per minute. So this goes around some 30 or 34 minute per scan or per sample. This is the, what can I say, the least setting that I can use. That is the It is not a very good setting, but it is the entry point of refinement. And I found that, by my own experiment in the machine that we have in the department, it's a Bruker machine, bench top. So in that one, if I go more faster than this 2.5 degrees, the pattern doesn't come out good for a refinement. The minimum specs that I need to use are this one. So this is what I use generally. If the better more the the optimal data taking or the optimal thing is around 6 to 8 hours per sample. This is, it will give you a very good data to fit on, because this data that I have, this was taken for a 10-minute scan, so it's not a good one. You can see a lot of background and then fluorescence, everything in this background, you can say. So this background has a lot of fluorescence. It is not good. If you take a very good data, this will more be a straight line, which will make refinement easier. Your mathematical model can fit very easily, and it will account only for the peak shapes, and it won't take all this noise into consideration. So the less noise, the better. This is how it is. For just to show it, if I have, okay, I'll show some fitted pattern or something. So for the same material, let's say the same rock salt structure, this is the pattern that I fitted, and it gave around some 1 point something to the this one, what do you say, chi-square value. So here you can see the background to peak ratio and all. Peak is more better as compared to that sample, and you see the background also, it's very straight line kind of. So I'll just compare both of this. I'll open it in the other legacy viewer. Both of these are same material, so just different machine and different settings. One is this one is this one. You can observe the background to peak ratio here and here. Here you have a high background, here you have a low background. This was taken according to this 2.5 degree per minute. This is the minimum I suggest, for my machine, I can say. But for different machine, I don't know. And the intensity you see here, 10,000, 11,000. It's not a very good, very less. Here you see it's 7,000, 70,000, 60,000 intensity. So that also matters to a great deal because your peak is very big and your background is very low. So that thing happens. So take good data, keep practicing your ritual, you'll eventually reach there. Have a good day. Bye.